give you that secondary carbanion type situation. If we took the alkyl groups off of either side, we've got symmetry first and foremost, which means no matter which side we eliminate with, we get the same thing as the other side. And here we're looking at the same level of stability for the partial negative charge regardless. So we would have to show both products as a result.
What if the amine was embedded in the carbon chain, where it was like carbon, carbon, and then H going down?
Let's take a look here. So you're saying, kind of guide me here, you're saying this,
and then there's an H at the bottom.
You want this.
And then it goes out. So where the two carbons on each side is positive. But then, let's say on the second carbon, the one on the left has an extra methyl group, so it's, nope, one more to the left. Sorry. There. How would Hoffman work here?
So Hoffman would be difficult here because any elimination that you tried, you'd end up plucking this first and foremost. So let's make that a methyl. And we, of course, would have to dimethylate it in order to get, if you can't get that ammonium species, then it's not going to work out for you. So looking at this, what you're comparing is not this and this. What you're comparing is this position and this position for the elimination, right? So we would favor this side because it'd be the least substituted, and that would give us a primary carbanion as opposed to a tertiary partial carbanion there. Now let me see if I'm going along with what you're saying here. What if I moved it out one more again? Right? Now in this case, we've still got that primary system versus the secondary. So if I were to take that out one more, then you've basically got the same exact stability on them again. Right? So unless there's a basis for a difference in stability of the partial carbanion, we'll get both as a result.
So it doesn't matter, like the first example, if we keep going off to the same, it doesn't matter. But if it's something like there where we have an extra methyl group on one side when it's asymmetric, it does. Can I get that right?
If it gives you a more substituted alkene on one side than the other.
Okay.
Absolutely.
All right. Yeah. So then we would end up with two products then, correct?
Well, in this case, not with the initial case.
Yeah, the initial case would not.
Yeah, the initial case, if we were looking at, if we looked at this example, we would end up with the double bond here and only there.
Okay.
Wait, would it clean?
Wait, no H, no B.
Hmm?
If it's elimination, no OH, no VR, there's no split. Okay.
Well, we're splitting, oh yeah, I see what you're saying. I was just using that to show you would be, we'd split here, absolutely. Yeah, so we would just end up with ethene. And then this would be our leaving group. And really that's not very different than what we see here, right? We just happen to have, I put all methyls on it. And so we're showing it as more of a detached. And the fact that all of these are methyl mean that there's no elimination that can occur at any one of those carbon positions. Once you get to 2 carbons or beyond, then we have to think about those from an elimination standpoint, because any one of those branches, right? So let's look. If I did, something crazy like this, now all of a sudden, I mean, this is a real problem. Because now we're looking at possible elimination here, 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 and here. That's a lot of different possibilities. But that's also why, most of the time when you see a Hoffman elimination, it is that methylated nitrogen that says, hey, we're going to focus on that parent chain, and we're not going to confuse or add to our difficulties. We're just going to use those methyl groups. This is, we can look at this kind of similarly to our alpha cleavage in our amines when we were looking at mass spec, right? How complex the amines can get. That make things better or worse? I can't tell. I'm not trying to read expressions.
So for that top one, if it were cut, it would cut. It could be either or would it choose the one with the more carbons?
So this would give us a dye substituted. This would also give us a dye substituted. So we really would get the same from both. So we get two products, two elimination products. We wouldn't have a Hoffman anti-Zaitsev product that predominated. But if I were to do something simple like this and take that methyl group off, now Hoffman on the left, right? We'd eliminate to the anti-Zaitsev here, preferentially.
So something like that wouldn't be on the test.
Something like this,
Yeah.
it could,
Be a great finish question.
but I think, you know, I feel like I'm in a good mood. So, no, I'm just kidding. This is an extreme, right? This is looking at it and saying you can make things horrible. You don't have to go to horrible to determine whether or not people understand Hoffman eliminations. That's what I'll say. Does that make sense?
In Hoffman, do we need to know like how they're building the iodine stuff?
Yes. Yeah, the ion exchange. So your silver oxide, you've got to have that. If you're doing a line reaction, remember that's part of your line reaction.
Could you show that?
Well, we've got that in our notes. It's just that line reaction. So we go through, all you have to do Okay, so how many steps on this line reaction? 3, okay. First step is what? Okay, methyl iodide, that's going to methylate. So our nitrogen is going to attack our electrophilic iodide, and it's going to add a third methyl group. So we'll have the ammonium, right? So it would be an ammonium iodide, but we said the iodide isn't a strong enough base. So we need to go through and do the anion exchange. What's our second step? Silver oxide. Which is what, formula-wise? Okay. And then what's our third step? Heat. Heat it up. Bring it to a simmer.
If you just had like silver oxide water and then heat as the second step after the methyl iodide, would that technically be wrong?
Now, what are you saying? Oh, you put heat and the,
Like,
uh,
or is heat like technically in of itself the third step?
heat is the last, it's after that silver oxide has done the anion exchange that we heat in order to cause the elimination, essentially. So we would have to separate it out. But I see where you're going with that. You said, well, we just don't want to heat it up as the silver oxide is trying to do its work, essentially. Yeah, the source of, you got a little bit of water here to give you that source of OH, essentially. Was that the question you had? Oh, yeah, sure.
Wait, is there a K2? Is there a K2CO3?
Hmm?
Is there a K2CO3?
K2CO3.
With the CH3I?
Okay. Yeah, as a result, you're talking at the end with your salts. The salts will just wash out, so we don't need to worry about that side. We're mainly focused on the appropriate alkene that we would get as a result.
If we're like on the first step, if we have like just like a secondary amine or something like that, do we need to list it's like excess methyl iodide or do we Is it just?
Oh, if we didn't have, so if you had a
Yeah,
hydrogen.
hydrogen attached to it, do you need to list?
Yeah, I would put excess, just to make sure. Yeah, just to let them know that you're going through and putting multiples
Okay.
in there, yeah. So his question was, hey, if we started out, you know, like this, we could then put in excess of our methyl iodide, and that would show that we were putting on multiple methyl groups. That would be fine. Does that help with what you were asking about? That-
Yes,
Yes?
So you don't even know the mechanism for BHA2?
like how the
We didn't show the anionic exchange mechanism. Yeah. That's the good stuff. That's the good stuff. Oh, front row's flagging. What else do we think? Yes? To open an oxide. Oh, okay. There really wouldn't be, they're gonna do the same thing. They're going to attack the least hindered position, right? Because they are basic in nature. Grignard is more basic than our Gilman. Where I would say the Gilman would be more necessary is if we wanted to add some type of alkynyl group, right? We can create more exotic Gilman reagents than we can Grignards to a certain degree, right? So you could create something a little bit more specialized with the Gilman, but they would do the same work, essentially. We just have less substituted position breaking open, and of course that would end up with the OH on one face and the attacking Gilman on the other face.
I have a question related to epoxides. So this also comes from like doing some of the back of the book questions. So sometimes I'll turn an epoxide into like a secondary alcohol, and that's like it. So like it maybe goes from ethanoxide to just like 2-propanol or something like that.
That would be with our LAH.
So yeah, that's what I was gonna ask. The back of the book, it usually just will sometimes use HCl, and it won't ever say like lithium aluminum. Like it won't put lithium aluminum hydroxide in.
HCl.
Like it will just throw in HCl and be like, this is good enough to turn an epoxide into an
Can you,
alcohol.
let's investigate. Let's look. I just want to put eyeballs on it because I want to know, before I make a sweeping statement, I want to know what I'm looking at here. Can you give me a page?
I should have written down a problem.
I'll put you on the spot there.
Oh yeah. Let me
Let's see, chapter 10.
have definitely had one here. Like it talks about the LAH, but then occasionally it won't use it. I guess is my question.
Yeah, the LAH is the only way that we know at this point. We've just sort of scratched the surface of our hydride reagents, but that's the only way that we know to get hydrogen as a nucleophile, right, or H minus to attack, because you know essentially what that ends up looking like is we've taken the epoxide.
Okay. I will look around for a problem because like I know
Okay.
it showed up a few times, but I can't like find the one specific that I was looking for.
Gotcha. So if I said LAH, and what's the molecular formula for this, or the chemical formula for LAH? Stands for lithium aluminum hydride. OH4, right? And so this is going to effectively generate hydride. So that's our hydrogen nucleophile. First time we've seen it as a nucleophile. And would we consider this acidic or basic in nature? I heard both answers. This would be negatively charged, we'd say it'd be basic, right? So we think of acidic as our proton, or H+, and our hydride is the antithesis of that, so that's our hydride. So that means that this nucleophile is going to attack where? The least substituted position, which is right here, and then it does this. And this will, well, and of course, I've managed to make something that's, there we go. I want stereochemistry. Now, all right, so if I just put in LAH, then of course this is the product, or one of, well, really that's the only product in this case because I had a very specific epoxide that I reacted with. But if I do the acid workup, oh, lost my juice. Now I've got my OH, right?
Now I got my OH.
So we'll have to see, depending on what you find.
I thought I saw one, but like I might have completely been seeing something else, like HCl pairs with like
Methanol or
methanol.
something
Maybe
like
that's
that.
what I was seeing, and I just missed the methanol.
That could be it. And that's, the reason I want to see those things is just in case, because that would be a big typo if they left out lithium aluminum hydroxide. We want to make sure we can see what's going on there. Now, if we had HCl, let's think about that one for a second, just as a practice. Electricity back here. All right. So we think about that one. HCl and methanol. What is the product of this reaction? What are we going to form?
Are you gonna attack? Yeah.
So we're going to create, let's think about our intermediate. So this is going to have SN2 and SN1 properties. Epoxides can be a little confusing in that sense, right? Because what we're looking at is the partial positive here, partial positive here. Which one of those is going to be more stabilized, the more heavily substituted position? And then our methanol, very similar to if we had water that would come in and attack, to put an OH group on there, will come in and attack here, right, and break that epoxide ring open. And then we'll end up with, now we'll have to have a workup, right? We'd have to have a base workup, same way that we'd have to have an acid workup for the alkoxide formation to protonate it. But we'll end up with this. Now, for this wedge, can I draw that as a straight line?
Yes.
We could, right? It's achiral. It is consistent. I would agree with that, right? So he said it's better to show the wedge. I agree with that so that we can see the stereochemistry of the epoxide in the final product. But if you just drew a straight line, that would be okay to the OH. Would it be okay to do a straight line to the OCH3?
No.
Absolutely not. We have to show the specific stereochemistry that came with it. Yes?
So instead of using LAH, couldn't you just use NaOH H2O?
Not to get just one alcohol, right? Because if we used our hydroxide, that would place, instead of placing, so let's think about, it's a good question to ask because we're looking at this position right here, and we say there's how many hydrogens there right now? There's 2 of them. When we look at that same position here, 1, 2, and 3, one of those coming from the hydride, right? If I were to replace that with hydroxide, then what I'm going to end up with is this, right? My OH, I'm going to get that 1,2-diol instead.
So the LAH is the only way to get like an alcohol instead of a diol from an epoxide.
Mhm.
Okay.
Yep.
But you can get diols from base
Acid or
reaction
base.
Acid, yeah.
Acid or base, exactly. Yeah, so we just have to think about it from the standpoint of what is our nucleophile and where does it add, right? And if we go back, I'm back to this and we say, well, this is our nucleophile, our LAH, well, that's gonna be one of those three. So we lose track of that. It's very easy to lose track of the hydride because it melts into the background because it's just one of the other hydrogens that ends up added to this carbon position, but it still is functioning as a nucleophile when it adds. So we just have to look and say, what did we add across this 2 carbon range?
So the hydrogen is strong enough to like kick off the oxygen in that sense?
Oh yes, yeah, hydride is a very strong nucleophile, very strong base. Very strong base.
This is kind of getting more broader stuff. I remember you mentioned it during office hours, but nomenclature-wise, we're not going over epoxides because we didn't really go through them during class. However, thiols and that type of stuff, and of course, the organic metallics are still fair game, correct?
Right, right.
Are there any other possible nomenclature things that may show up on the test besides previous stuff we already went through?
Not besides previous stuff, no.
But she said that LAH is the only way to get what?
To form an alcohol rather than a diol or an alcohol ether, right? So it's adding something, it's adding a nucleophile, but that nucleophile doesn't create, doesn't add on a new oxygen or nitrogen or halogen group. It just adds a hydrogen to it. Yes?
This might be dumb, but when you are given like 2 things like HCl and then the methanol, like how do you know which one is like attacking and which one's dictating the conditions?
Well, so our acids, so we look at that, okay, that's it. So when we look at this, we say HCl and methanol. Well, methanol will be our neutral solvent species, but this is what we call a solvolysis reaction, right? So that's going to be in abundance. We're going to have a lot of that. HCl, how do we, I'm trying to think of a definitive way that we would know rather than, you just know, because that isn't helpful, obviously. So we look at this, and when we're seeing these things, sulfuric acids, HCLs, unless they are listed by themselves, right? They're in support of some other nucleophilic species, right? HCl by itself can protonate an alcohol, and then the chloride can come in and attack. But if we have HCl in a solvent system like water or like methanol, even though we have that chloride available in solution, there's so much more of the alcohol, whether it be water, whether it be methanol, ethanol, that's going to act as our nucleophile first.
So every time it's printed, it's other things in the file.
I don't want to say 100% because we know that there is no 100%. There are exceptions everywhere in this, but that's the way we can look at this situation, because we know that oxygens, alcohols, and epoxides, the way that we can activate them, one of the simplest ways that we can activate them to make them better leaving groups is in an acidic environment. So when we see hydronium, when we see HCl or HX, and we see sulfuric acid, we know that the oxygen's waiting to grab it to form a better leaving group, and then something else can come back in and attack, whether that's going to be the halide, whether that's going to be the alcohol. We'll have to see.
So then for the LAH one, how did you know that like the hydride was like dictating that it was basic conditions and also doing the attack?
Well, that's because that's all that reagent will do, right? So the lithium aluminum hydride, all 4 of those hydrides, it's actually a 4-to-1 ratio that we have here. There are 4 hydrides that can be delivered, and that's the only form. So they are not acidic in any nature, in any way. It would be paired with, if we saw it with a, let's see, it would be ether. Very similar to our Grignards, our organolithiums, it has to be in an aprotic solvent system. Because if I threw it in, I couldn't do LAH and water. That would be horrible. Really bad. It's happened in the chemistry department years ago. And you've never seen panic when all the sprinklers go off on an entire floor for a lithium fire. It's quite brilliant, as long as everybody's okay. So one of the grad students had accidentally left it out where moisture could get to the LAH, and it just started to burn and burn and burn. Now, what does that mean for your test and looking at the line reagent? I don't want you thinking about that during the test. But the idea is that think of it in the same way that you would the Grignard that says Grignard, no water, no alcohol, nothing protic, LAH. And we're going to see sodium borohydride is a little bit different in the next chapter. We'll say LAH has to be an ether, no water. Okay, what else do we think?
Could you go through an ether cleavage when they're both primary?
When they're both primary, you would cleave on both sides.
Okay.
Yeah.
And so then the ones that will be asked to only do one side is if one of them is more substituted than the other.
And the two extremes obviously are going to be the simplest when you're looking at a tertiary versus a primary, something like that, or even a tertiary versus a secondary. But the more heavily substituted side will take the carbocation and then the halide will attach to that position.
And you could even have like allylic or
Yeah, you could. Yeah, so if you have an allylic system, right, so that turns the more heavily substituted on its ear a little bit. That says, hey, I could have, let's do that. Right, what if I had an ether like this? And you say to yourself, I'm looking at this position, I'm looking at that position, and we'd say, oh, well, that's a pseudo-secondary, and this is a pseudo-primary, but it's not just a pseudo-primary, it's a pseudo-primary allylic. We could do the same thing with bazylic, right? Benzylic, I should say. So this would be our more stable carbocation, so that's where our carbocation would form, the other side would form our alcohol as a result.
And then what about secondary allylic versus tertiary? Would secondary allylic be?
So the way our carbocation stability goes, methyl and vinyl, bad, primary, secondary, tertiary, primary allylic, secondary allylic, tertiary allylic, right? So we view our primary allylic as being pretty close to the, but still a little bit more stable than our tertiary. Secondary allylic, much more stable than the tertiary. Tertiary allylic, the most stable of all.
So if it's allylic, it's always more stable than one that's not allylic.
Yeah, I think that's a good way to look at it. Unless it's benzylic. That technically wouldn't be allylic.
Yeah.
Yes.
In ethers, when we have secondary as our highest, is that going to be SN1 or SN2?
Big.
Is it going to be SN1 or SN2 if it's secondary?
If it's just secondary versus primary? That would most likely be SN2 on the least hindered side, which would be the primary side. It's tough to make one of those secondary carbocations to go through an SN1. That would be kind of difficult. What do we think? Yes.
Secondary SN1 or SN2 reaction when it's ethers?
It is typically SN2.
SN2.
SN2 for a secondary system, it's hard to form that carbocation. Hard to form that carbocation in a secondary system. The book tends to show some of that formation, but it really is, unless we're in a conjugated system, it's tough to do. So you would go SN2 at a secondary position, but if you had it paired with a primary like we do here, well, if I took away the allylic, of course, it would do SN2 to the least hindered side. If it was going through an SN2 format. Yes?
So you're saying if you have a secondary on one side of the ether and a primary on the other, then the glucose will attack the primary?
I would attack the primary, we'll go through we'll protonate to activate the oxygen, and we'll attack the least. What did I just do?
You just touched the next one.
Go away. Get out of here.
Hey, we're bringing out the hurricane.
So, what was I saying? Secondary versus primary, we protonate to activate the oxygen, and then we have our nucleophile come in an SN2 fashion at the primary position to then split at that position, giving the OH over to the more substituted side.
So the book said like for primary, would it be SN2, and then for secondary and tertiary it would be SN1. So are you
Yeah, that's implying that the carbocation would be feasible for a secondary, but they're not very stable at all. So I would look at those as SN2s.
If it's SN2, like why would it still not just attack the secondary side?
Because the primary side is less sterically hindered. So SN2 always goes to the more easily accessible side. It doesn't have as much to navigate through, essentially.
But then for like alcohol substitutions, secondaries go through SN1.
For alcohol substitution, give me a, for instance,
Well, like I don't know, 2-butanol,
uh,
and you wanted to, put on a bromide, and you said like HBr and heat, that would be an SN1 reaction, not an SN2 reaction.
I would still look at that as largely an SN2, but I wouldn't use HBr in that case. I would use PBr3 every time, because that's going to give you the SN2, will invert your stereochemistry instead of giving you the mixture of the two products.
So on the exam tomorrow, are we expected to understand that secondary will go through SN2 reactions?
I would say yes, because it's very difficult to form those carbocations.
Okay.
Very difficult. And that's why HX and heat is not a good way to convert an alcohol into an alkyl halide.
Okay.
Right? If you're talking about a tertiary, then great. Because you're talking about a carbocation that forms and is one of the more stable, non-conjugated systems that we have. But if you're talking about a secondary, it's a lot tougher, and going through the SN2 is ultimately going to be the better option.
Okay.
So on that note, then, if you're given a question to where we have that type, where we have the reactant being there, and then we have the alcohol on a secondary, and then we have the product being the actual one with the halogen, you would not suggest us doing HX, you would rather us do PX3.
Yeah, or a vinyl chloride, something like that. I think that would be a better, it's more predictable on a secondary or primary system. And remember, the mechanism is SN2, the final conversion is SN2, so we couldn't use it for a tertiary, but we would need to because HX will work just fine on the tertiary system. But for a primary and a secondary would be useful, the most useful.
So an ether that has a primary and a secondary, it's gonna form the alcohol on the secondary one and not the primary.
So an ether that has a primary and a secondary,
Like,
can be blinded by that.
like there's a primary on one side and there's a secondary on the other, and because you go through an SN2, then you're gonna attack the primary side and form the primary.
Yeah, if you go through an SN2 mechanism, you go to the least hindered side, which would be the primary.
Okay, and so that's why it matters which one on the ether.
Right. Okay.
Because you're going to
Yes.
Does this apply for like everything that was like in the book where it was like secondary and SN2?
Oh, not
That's
alone.
in every other reaction.
I never say always, you just can't do that 100%. All right, what do we think? We ready?
Can I ask one more question?
Sure.
I don't know if you can answer this.
Uh-oh, and I probably can't.
Are there any questions that we should have asked you that we have not covered that would be very useful for the test coming tomorrow?
Trying to trap me. I will not be trapped. I'm elusive. No comment. This press conference is over.
Fair enough.
Probably. Is
Probably.
that a glib response? No, I don't think. These were all great questions. Everybody's going down the right path with the level of understanding that they want to have. So you guys are, sounds like everybody's on point. So that's good. Good news for me, good news for Richard. So the other Richard, not the third person. study for another evening. We'll see you in class tomorrow, okay? We'll finish up chapter 11.